Um, Welcome everybody. So today I want to talk about PID loops or PID control. We've teased this a little bit earlier on in the quarter. It's something that's really important in industrial process control. Now, once again, I want to make the disclaimer that I am not an expert on this stuff. I went through 157 at Davis. I've seen some implementations in the field. I feel like I have a pretty decent general understanding of how this stuff works, but I'm not an expert, and I'm not trying to replace what you're going to learn or have learned in 157. But I'm going to briefly give an overview of the concept of how this works, and then go into trying to show how you would program it on the CLICK PLC. And then probably next Wednesday, we'll test it live. A, because it's going to be time consuming. It'll give me a chance to troubleshoot it. And B, because I haven't rewired my wall today, so we can't actually run the motor. Okay, so PID stands for proportional integral. Yeah, like the math integral derivative. Also like the math derivative control. So you can have, in these controllers, you can have just a proportional response controller, you can have a PI, or you can have a PID, or you could have a PD, I guess. But you pretty much always have to have the proportional response. So what does that mean? So let's say you have what we have, where you want to set the speed that your motor is spinning. So for us, your operator, or sorry, your motor is rated for up to 60 hertz. That's the AC frequency input. And that is should be equal to 1725 RPMs. Right, and that information is straight off the side of the motor. It has a sticker on it that gives you this information. Okay, so for us in our system, in previous exercises, we've programmed a system with an HMI. That's your human interface. And that takes basically your Bob puts in 0 to 100. Should have made this bigger. Bob puts in 0 to 100% on the keypad, right? And then there's a tag in the HMI that sends that value to the PLC. And at that point, that's still 0 to 100%. Okay, and then the PLC takes that input value, which is a digital value. It's a digital, I think it's an integer, it might be a float, whatever. It's a digital value, and it outputs an analog signal of 4 to 20 milliamps to the VFD, which is our motor controller, right? This VFD takes that analog signal and translates it into an output to our motor itself. That output can be 0 to 60 hertz, and that motor should spin at 0 to 1725 RPM. Okay, so this should all be something we've already talked about at one point or another this quarter, right? All of this process here. We've programmed this, we know it works. However, what what did we see on the actual RPM for the motor when we configured this and ran it? That is a question.
Fluctuating value.
So it fluctuates, right? And that's normal in any process. You know, you would expect it to drift a little bit, and that may be your actual process is drifting a little bit, which is normal, or your instrument just has some inherent error bounds in it, and so the value you're reading on that instrument into your controller has some chatter in it, right? That's totally normal. Now we had to do some things in the ladder logic that I probably didn't go over in very much detail to kind of smooth that out and try to get rid of that fluctuation, but it's still going to be there. But what I was looking for is in our measured value, which I actually believe to be correct, we saw that this motor was actually spinning at about 1775 at when we gave it 60 hertz, right? Which could be due to at least two different things. One could be this VFD is actually putting out a higher frequency than 60 hertz. That's a possibility. I don't think it's very likely. The other possibility is that the motor windings just aren't that precise. Or you have instrumentation failure. Wait for it. Okay. So yeah, so this could be internal to the motor. You know, the windings could be a little bit off. That would be my guess as to what's causing this. Or the third option would be our instrumentation just isn't that accurate and we're just getting a little bit of a high reading because we're using tape and a photo eye when you should be using an encoder. It doesn't really matter though. Let's just assume, for the sake of argument, that this high reading is actually true. Our instrumentation is good, and there's a you know, slight manufacturing tolerance in the motor that's producing a little bit too high of rotation speed. That's fine. This is, you know, this is a economy scale or economy grade motor. It's not super high precision. You know, it's tough and it's durable, and for the applications for which you would use it, you're really not gonna need that kind of precision on your rotation speed. But let's say you do. Let's say you want to use this motor and you want it nuts on to run exactly how or exactly at the speed you've set, right? So I jumped the gun here. So we're inputting 0 to 100%, right? And you can directly translate that to RPM. So basically 1% on the input is equal to 17.75 RPM, right? Which is basic math. So now we have our little fork sensor. He's reading the motor speed, and we're feeding this back into the PLC. Now, this is simplified because really this is a discrete input that just goes on and off, and then we're doing a bunch of math and timing in the PLC. But let's just, for the sake of simplicity, this is, just pretend like this is an absolute value of the motor speed. Okay, so now the fact that we have this feedback allows us to implement a PID control loop. And so what a PID control loop is, from a generic sense, or kind of a generic overview, is you have your process variable. For us, the process variable is, you have your set point. Okay, that's from your operator. That feeds into your algorithm. Okay. I'll talk about that block in a little bit. Forget what this is called. We'll just call this algorithm. ALG for algorithm, right? So we're going to call this my math box. Now, in 157, you will spend a lot of time doing Laplace transforms and some really super awesome math to derive what the internal math of this looks like. For us, we don't really care. This is a super simple loop. Well, I'll get into this more in a minute. Okay, so you have your algorithm that produces a output, and then that output basically gets split. So this basically goes to the field where a change gets implemented. Okay, and so in our case, well, let me talk about the split first. So this split comes back, and I forget what the term for this is, but this is basically your deviation. So this is your difference, this output, when it goes through this algorithm, this is your difference between your desired process variable value and your measured process variable value, okay? And so this goes up here, and I think the convention is this is negative and this is positive. So you subtract this deviation from your set point, and then that goes through the algorithm, and that produces your output, and this is your control loop. Now this is super simplified. Again, don't take this as the Bible. You'll go through, or you've gone through 57, you know what I'm talking about, or you're going to. So this is very simplified, but basically what I want to show is you take an operator set point in, you run it through your algorithm and compare that to your field value. You compare the deviation and you change your output. Now this output to the field, in our case, would be you have your set point coming in from your operator. That's 0 to 100%. And then when you go through this, your field output is going to be 0 to 60 hertz. Because remember, all this is happening in the PLC. It's going to be 0 to 60 hertz to, it's going to be 4 to 20 milliamps to the VFD, and then the VFD is going to output 0 to 60 hertz. So that's kind of another block out here. Okay. So to implement this, I need my set point, which is my user input. I need my process variable, which in our case is that discrete input into our math function, which outputs RPM. That's our measured field value, right? And then you need the tuning parameters for this algorithm. And that's basically it. And so what this does is this loop executes, I think, multiple times per millisecond. It depends on your controller. But basically this algorithm, or this control loop, keeps running and keeps processing through this algorithm. And then it keeps measuring, at the end of the day, your motor speed as a feedback. And it's monitoring that. And so what it's doing is it's going to keep changing this output value in small increments until this motor speed that it's measuring matches the set point input from the user. Okay? And it just keeps doing that by iterations. So in that process, your P is your proportion, is also known as gain. And this is the same as like gain on an amp. So for every one unit of input into this thing, how much do I change the output, right? And your gain can be Actually, I guess you could have a negative gain. So in theory, your gain could be really any value. The sign will really be determined by how you set this up. And I'm not going to talk about that because it gets complicated. But basically, it's like if you're taking a 4 to 20 signal in, right, for every 1 milliamp, how much do I change this output response? And that's determined in your algorithm. And that's called your gain. And then the integral term is a little more complicated, but basically, if you just have a straight proportional controller, and you have, so you have your system, and this is the process variable, and this is time, and you introduce a set point change. So let's say this was 1, and you want it to be 2. Your system will respond, but if it's just straight proportional, there's always going to be some offset between your set point and the actual field value of what it reaches if you just use a straight proportional controller. This has roots in the complicated math that you'll learn and discuss in great detail with Professor Ellis. But basically, introducing your integral term, your I term, does some cool math and gets rid of that process, or gets rid of that offset, in theory, if you tune it correctly. So I gets rid of offset. That's all you really need to know. Now, again, when you're configuring this, you need to tell your controller what your P and I values are, right? You have to program that. It can't just figure that out for you. And so your gain, your gain will also determine, so in this curve, you know, there's a certain amount of time from, let's say I made, this is T0, when I made that set point change, there's a certain amount of delay, and then there's a certain time response from here to here before it really like reaches the new steady state. That's called your response time. That's directly determined by your gain, your proportionate value. So hopefully that's making sense so far. There's all kinds of techniques you can use to determine these values. Generally speaking, for something super simple like us, we're just going to set P and I to 1, I think. And we'll test this and see if we can get it to actually work, and we can play around with the response time and see if we can get different response times out of it using different values for these parameters. But for something simple like this, you're basically just doing a directly proportional response. Okay, so that was that screen. Okay, now before we dive into how to program this in CLICK, I just want to talk about a few things. I'm going to post this code onto the files in Canvas, and I'll make an announcement. You guys can look at it. This is how I programmed the motor control and RPM meter. This isn't, you know, the absolute right way to do this, but to the best of my knowledge, it's a pretty good way to do it. And you'll see that I also included interface with the HMI in a couple points. And so here you see we're monitoring contact 1, just to see that status of the virtual switch that I programmed. Here, DF10 is the VFD percentage input from the HMI. That's where your operator types in their desired speed. And I'm reassigning that to DF5, which, as you may remember, is the analog output on our PLC. So this is a common, you'll see this commonly where you take one value that the user inputs and you then write it to a different different data register that actually affects the field. There's a lot of different reasons to do this, but this is a best practice. I highly recommend doing that, especially when you're getting an external input of a value. One reason alone is just that if your external input device dies, then you can set this DF5 to be retained. Anyway, it doesn't really matter that much. So you got your timer block, and then you got your counter block. Most of you guys program this pretty satisfactorily in the homework. And then you have your math block that's calculating your motor speed based on those other blocks. Then I think I went over this. This is basically a really crappy buffer system that I created that keeps that RPM value on the HMI screen from fluttering too bad. I'm sure there's much better ways to do this. This does work though. And then it writes out that motor RPM speed back to the display on the HMI. Okay, so that's our starting code. Now, as it is, this just operates in what you would call open loop, where it just writes a value out into the field and hopes that we hit our target, and that's the end of it. There's no feedback control of this process. So we are measuring the speed of that motor, but we're not controlling it based on that feedback. So that's where our PID comes in. So over on the left, you can see PID monitor configuration. If you just double click on PID setup, it'll pop up this new, this PID configuration. So in here, you have to select big chunks of memory that this thing uses. So to be perfectly honest, I'm not sure how other manufacturers handle this, but for CLICK, it just says, okay, if you're going to implement this control loop, I need these data registries. These are default. This is what I'm going to use. It has to do with error codes and set points and everything that this everything you could possibly program this PID loop to use, basically. And so from that sense, it's kind of nice because if you know the selected range of data registries, what the heck? It's freezing up on me, sorry. If you know the selected range of data registries, you know, it starts at C100, then you know all these PID loops use the same indexing for their data registries. So you know, alarm Bob stuck his finger in the motor is always going to be the 5th block of memory that was assigned to that. Sorry, this is freezing up. Oh, looks like maybe we're back. Nope, it's still freezing up. That's not good. Okay, well, while we're waiting for that to fix itself, any questions about what I've talked about so far? Okay, I'm gonna kill this and restart it. So clear as mud, you guys got it? No problem? This is why we post them. What's that?
I believe so. I had to break the silence.
Yeah. You guys probably know this better than I do at this point from sitting through 157. Okay, so let's try that again with the PID setup. Hopefully it doesn't crash on me again. Okay, PID setup. Don't die. Okay, so you go to the address picker, and then when you're setting this up, I would recommend picking memory locations that are kind of like later on in the set of available memory, just because that way you don't have to worry about interfering with it. So I'm gonna start in the 500 range, just for no other reason than it's way up there and I'm never gonna have to worry about it. So okay, so I set my contacts to be 500 through 540 or 501. I'm gonna set my DS to be, again, 501 through 515, and then DF, I'm going to go to the 400 series. Not a lot of floats available. Okay, so I've selected my memory that's going to be assigned to this thing for my set point. So if you remember, you can see, well, actually, you can see this diagram, or that PID loop. So you have your set point coming in, you have your algorithm, you have your output to the process, you're measuring the process and feeding that back as your process variable. And so this is really nice because it's just, you can click through this interface and configure everything. But important thing, my set point is DF401, okay? I need to remember that. Now, it's not really a problem because this is already limited. Your input range is already limited on your what am I saying here? It's already limited on the HMI, but we're going to go ahead and limit this to be 0 to 100. Now remember, this is a percentage, which means our process variable coming back in that we're measuring also needs to be a percentage. So we could have this set point be in any scale we want, right? But you always got to compare apples to apples. So if your set point is in RPM, your process variable feedback needs to be in RPM, right? If it's a percentage, same. If it's a 4 to 20 milliamp, they both need to be 4 to 20 milliamp, right? In our case, we're going to do percentage. It's easy. We don't really have to worry about it. So in here, if you click on loop algorithm, you have to set the PI and D. So you can set these to whatever you want. Like I said, we're going to start with 1 on the P and I. I didn't talk about derivative, as Professor Ellis says, this is some black magic voodoo. Don't worry about it. He'll explain more what that is when you take that class. And then the output is set. We already set. So I guess by default, it's just set to a percentage. That's DF409. And that's going to be our output that we feed to the VFD. And then our process variable is our measured input of the RPM. And so for us, can anybody tell me a problem we have right now on this screen that you can see with the process variable? Okay, I'll tell you. If our theoretical maximum for the motor speed is 1725, and we're measuring 1775, is that greater than 100% of our operating range? Yeah. Yes, it is. So we should probably set this upper bound for the process variable to be more than 100%, right? So what that means is we need to translate our RPM into a percentage somehow. And we could actually Now that I think about that, we could actually do this right here. But the thing is, like I said, we want our process variable to be the same units as our set point, which is a percentage. So we're going to leave it like that. So we're going to leave the PV upper limit as 110. Okay, so now I'm going to hit OK, and this is going to create this loop. And so if you go back, this loop now runs in the background of the program, right? It doesn't mean it's correctly implemented with the code we have. What it means is it's going to do its thing, namely try to manipulate its output based on whatever feedback it's getting on PV to try to make that PV match your set point, right? If we don't set up those values to be correct in our ladder logic, this won't work correctly. And so that's what we're going to look at now. So first thing, we have our user input comes from DF10. And right now it's being directly assigned to DF5, which is our motor output. Okay, that user input should be our direct set point value. So if we open up that window one more time and we go to set point, our set point is DF401. So I'm going to change this to DF401. Okay, so that just means if my user types in a new number on the HMI, it gets written directly into the desired set point for our PID loop. And the cool thing about this CLICK software, you can see right here, it's telling me, hey, by the way, this is the set point. This data register, DF401, is the set point for PID loop 001. The nicknaming and stuff that it does by default for that is pretty nice. I like it. And if you go into your address picker, you can look now. You see all these values that got assigned here. They all have nicknames, so you can go in and you can just read what they are. So there's a lot of alarms actually. And you have to actually configure what those do, but it's creating these memory locations by default so that as you're programming these things, if you go back later and you're like, oh crap, I want to set a high alarm on that, but like I didn't allocate memory to it, and so now when I allocate memory, it's going to be this other block of memory that's not a contiguous number with this memory block that I have to the PID, and your shit gets all scattered and it's no bueno. So that is a nice thing that that this software does for you, is it's like, hey dummy, you have to have this block of memory. You don't have a choice. You may need this stuff later. I'm making you do it now. So that's just kind of a side note. Okay, so now we have our set point feeding in. Now we need to feed our process variable we need to feed our measured process variable back into the PID loop. And so the way I'm going to implement that is I'm going to use a math block, because if you remember, a math block lets you do two things. It lets you do math, as the name implies, but it also lets you write a value into a point in memory, which is one thing we need to do. We need to copy that measured RPM value into our PID loop. So I probably should have just written down what my critical points in memory were. So let's see, my out is DF409 and my PV is DF412. Okay, good to know. So now, so I know this block right here is copying my measured motor speed into the HMI for display. And I know going through this exercise, I've basically buffered that so it's a semi-stable value. Because it's really important, well, there's different ways of filtering your input in a PID loop. This is a manual way to do it. There's actually conditioning you can program into the loop, but it's kind of important to make sure, like if your process variable measurement is jumping around like this, your PID loop is going to jump around trying to compensate for that, right? And so sometimes you can get an imbalance in your system where your controller is seeing this and it's doing this, and then it causes your field equipment to just take off and explode, right? Super bad. You'll learn about that in 157. I talk about stability criteria a lot. For us, we've already kind of stabilized this measurement of RPM, so we don't really have to worry about it that much. So what I'm going to do is I'm just going to say, well, I'm going to take that DF11 because I know that's my stabilized kind of flat RPM rating. Assuming my motor is running at a constant speed, that DF11 value shouldn't fluctuate much, right? It might jump a little bit based on the way I have this set up, but for the most part, it should stay fairly steady. So I'm going to use that in a math block, and I'm going to assign, so remember this is my process variable. So I want to assign DF412, my process variable. I want that to be equal to DF11, which is my measured motor speed, divided by 1725, which is my theoretical max 100% motor speed. And so what this is doing is it's taking my measurement, it's dividing by my max, that's a percentage, right? And so this should range from 0 to 100, although we know, we just talked about, it's going to go slightly over 100 because our motor spins too fast. So we might get, I didn't do the math, I just made it 110% on the max bound because I know that's way more than we are over. I think it's like, off the top of my head, it's like 1 or 2% over 100. Okay, so now I'm inputting my process variable measurement into my control loop. The last thing I have to do, and I'm just setting this to run constantly. I don't want this to execute conditionally. I want this, no matter what, always be writing into my loop. So now my last thing is I need to, so I have that PID loop is always running and it's always putting out its output and it's always writing that output into a data register, right? But what is that data register doing? Right now it's not doing anything because it's not assigned to do anything. So all I'm going to do is do another copy block, and I'm going to take the PID loop output, which is DF409, and I'm going to copy that into my physical 4 to 20 output, which is the VFD, which is DF5. Okay, so now, assuming I did all this correctly, we are reading a user input on this line and feeding it into the PID loop. We are measuring our field process variable. I mean, we're doing a bunch of stuff to it all in here, but we're measuring that and writing it into our PID loop right here. And then right here, we are taking the output from our PID loop and physically making that an output to our field equipment. And then that cycle just runs in perpetuity, and hopefully it dials in our motor to the exact speed that we have, that the user set, which again is limited both in our PID loop and in the HMI to be 100%. Now, there's one important point I want to make, which is that you could potentially want your output to be more than 100% of what your actual set point, what your actual maximum set point would be, because of physical disturbances and inhibitions in your system. So what the heck am I talking about here? Well, in our case, right now our motor's running too fast. But let's say that you have your motor a little box, it's getting a wire, it has an output shaft, and that output shaft is hooked up to a conveyor system. And there's some resistance on this conveyor system. There's stuff rubbing on it, and I'm just going to put a box that's a big heavy box that's slowing it down. So if you output, let's say, 100 RPM, right? And if your motor, and you had this all tuned up to where your motor will spin 100 RPM if there's no load on it, there's no resistance. Well, all this resistance, you might actually see like 90 RPM, right? And so if this were the case, we would actually, to achieve 100 RPM, we would probably want to set this to like, I don't know, 112 or whatever. That would be our input to the motor, or our output from the controller. So in this case, if 100 RPM is your maximum RPM you want to spin, then you might want to set up your control loop to allow your output to be more than 100%. Because that's the only way you're actually going to achieve your 100% output of 100 RPM due to these physical resistances. Now, for us, that shouldn't be a problem. We're actually having the opposite problem where our motor is spinning too fast, and therefore we probably don't want our output to ever be more than 100%. Another point of fact, our VFD won't put out more than 60 hertz. So even if we told it to do more than 100%, it can't put any higher than 60 hertz out, and it won't. So that's another important point, to limit your output into a physically logical bounded range. Because if you try to do something with your controller, you try to put an output with your controller that isn't physically achievable with the hardware you have, then there's no way you can ever get your controller tuned correctly, because you're always going to be trying to do shit you can't do, right? That was very fast. Hopefully that was cohesive. So I think the code as I wrote it will work. I have not tested it because I didn't rewire my wall, and we can't do that today. But on Wednesday, we can re-review that code we wrote today if you want, and we're definitely going to test it and see if it actually works. We got 7 minutes left. Questions, comments, abuse, concerns?
As a comment, I have heard that the derivative part of PID is pretty much not used. It's not very common.
You've heard that from Professor Ellis?
I heard that from my roommate who's going to do that, from someone who, his interviewer basically, when he was getting his job.
Okay, cool.
So he's like, his interviewer said he's worked there for like 30 years and he has never used derivative and has no clue what it does.
Nice. Yeah, that all of the math that goes into your algorithm comes from Laplace transforms, and those of you that have taken the class, it's gnarly math. You get some really interesting stuff. And you can't really relate the Laplace function directly to the physical or the time domain, right? So yeah, I can't tell you what the derivative term does either. In my extremely limited experience, that is true, what Andrew said. But sometimes you need a little black magic voodoo in your life.
So that 112 number, that's RPM, not percentage, right?
Yeah.
Okay, cool. Just making sure.
Yeah, I just, for this example, let's say 100% is equal to 100 RPM.
Yeah, you wouldn't get full capacity.
Yeah.
Okay, cool. If it was percent, I would have been really confused.
Yeah, but your controller, like to achieve 100%, your controller is equal to 112% output, right? But again, this assumes that everything between your PLC and your motor can actually output over 100%. In our case, it can't. It physically cannot. And so, and typically, you know, you're going to define your system like if it's valve stem travel, right? That's a physically bounded value. You can't get more than 100% open on a valve. And so you actually need to bound your process outputs. And actually, for a lot of times on a control valve, for various reasons, you might set that from like 10 to 75%, right? And this is to avoid cavitation or like a runaway in your process, or various different reasons, right? But you might set this bound in your control loop. That should make sense when you take 157 and 158. Oh, remember this moment.
That makes sense now.
Okay. So this this right here is actually really rewarding for me, because talking about these things in concept is actually helping me tie together a lot of things we've talked about in the senior level classes at Davis. You know, I feel like I understood the things conceptually pretty well in the classes, but when you start talking about how would you implement this in a controller, it's really making things click better for me. So hopefully y'all are getting the same experience. And hopefully Professor Ellis takes up my generous offer and actually uses this hardware as like a optional lab demo.
Question, John.
Yeah.
Have you done the PID configuration before on the software, or this is you had to do it like recently, like before you? When did you like know how to do this stuff?
So I formally learned how to do this in 157. At least like the broad, or not the broad, the detailed conceptually what you're actually configuring. I learned that in school. I've had exposure to and, you know, played with tuning PID controllers before. I knew I knew what they were used for, right? So like on an air handler, you know, I helped basically calibrate airflow for a clean room by setting the parameters in a PID loop. So, you know, we played with the P term for speed of response, and then we set the to the minimum and maximum flow rates that they needed for that application. But in terms of actually programming this on the CLICK, I mean, I played around with it before today, but this is probably the first cradle to grave PID implementation I've ever done, if that answers your question. And it has yet to be tested. I'm pretty confident this will work unless I goofed up something on the scaling. And that's why I made such a big stink about like, make sure your process variable and your set point are apples to apples, because if they're different units or something, this will explode. Hopefully in a fun way and not a physically damaging way. All right. That's our official time. Anybody have anything else? All right, I'm going to stop recording.